Okay, well, I should have asked. I assume everyone can see the slides. I know Jordan can hear me, so I'm going to assume everyone else can hear me. Oh, there's Boyson. Perfect. So under the assumption that everyone is able to see our slides and is able to hear me, I will begin. So we are going to continue to work through lecture set number 3. And lecture set number 3 is about it's about deriving the general process for estimating the parameters of a generalized linear model. So what we're trying to do here is sort of get under the hood, if you will, to understand how these models are fitted in practice. Now, as we know, for the most part, when we're actually using these models, the fitting process won't be as tedious for us because we're going to be using built-in R functions that run these processes in the background. But what we'll learn is how these processes actually work. And in later labs, we'll actually see comparisons between the fitted model and the built-in functions and how those values align. So what we're trying to do is give insight into what's actually going on behind the scenes or within those functions. Okay, so first off, last lecture, when we started lecture set number 3, we introduced the idea of maximum likelihood estimation. So that is, we're going to construct a log likelihood function for the model that's of interest to us, and we're going to find the, given a parameter for that likelihood, we're going to find the point that maximizes that log likelihood function. So basically what we're trying to do is, given some monotone or given some curved structure or function, probably function would be the best word, we want to find the point that gives us the maximum value of that function. Now, a lot of the time, the models that we are going to work with aren't going to have closed form expressions for their MLEs. So what I mean is, suppose you want to estimate the parameter for a particular distribution. That parameter is you can't find an expression given just the data for that particular parameter. So in order to find an estimate of the parameter, you need to use an iterative process. So the iterative process, that's one of the common iterative processes for finding a maximum likelihood estimate, is the Newton-Raphson. The Newton-Raphson basically says, take an initial guess at your MLE and then add the value of the score function divided by its derivative and push that value closer to what it should be equal to, or to the actual solution. You could also take that value and add the score function divided by its information function. And those exact formula are given on slides 4. So here's the initial guess, theta at k minus 1 minus the score function divided by the derivative of the score function evaluated at that number. And then here's the other representation, theta k minus 1 plus the score function over the information function. Okay, so we have these two different representations for the Newton-Raphson for finding our MLE. What we started working on last class was an illustrative example of how the Newton-Raphson would actually unfold in practice. So we have a Weibull distribution, the density of which is shown on slide 6. What we're interested in doing is maximizing for theta, given lambda is known. We're going to specify a value of lambda a little bit later. And in order to do that, what we have to do is first derive the log likelihood function. Then we have to derive an equation for the score function. We'll notice that that score function cannot be solved directly. So the update for theta cannot be found directly. So we need to employ the Newton-Raphson, and then we're going to set that up. So we have 49 observations measuring time to failure in hours. And we want to fit a Weibull distribution to this data set. And we want to find the value of theta that maximizes the likelihood of this particular distribution, given the data that we have. Okay, so the last thing we did on Thursday last week was work out how the Weibull distribution belongs to the exponential family. This is going to be valuable to us in a couple of slides because when we go to derive the information function, we can find it using the formula or the relationships that we worked out last class, given that it's an exponential family member. It's also good practice because we know that the exponential family is one of the response variable belonging to the exponential family is one of the components of a generalized linear model. So this also serves as additional practice in just writing things in their exponential family form. Okay, so we have our density shown at the top here, and we were tasked with putting this thing into its exponential family form. We note that this is not in canonical form. So that means that the Weibull distribution would not be suitable for a generalized linear model, but for the purpose of illustrating the Newton-Raphson, we can still use this model. Okay. So we have a of y, b theta. It should be negative theta, negative lambda. I just had lambda there, but there should be a negative given that the last term is negative y over theta to the lambda. Then we have c theta is log lambda minus lambda log theta. And then we have dy lambda minus 1 log y. Okay, so this is the Weibull distribution in its exponential family representation. And it's not in canonical form because canonical form again means a of y equal to y. All right, so the next thing we're going to do is try and work out the MLE. So we know that this is inevitably going to turn into an iterative process because that's the purpose of the example. But theoretically, what would happen here is we would derive the score function. We would set the score function equal to 0, and we would try and solve for theta. Okay, so we have worked out the log likelihood function for an exponential family member in lecture set number 2. So we were able to show basically that the log likelihood function for an exponential family member is ay, well, I'll just write it down here. So we have from lecture set 2, the log likelihood function for theta given lambda y in this case is going to be equal to, and we're going to have, we have 49 observations, so we're going to need to consider the sum in this case. All right, so we are going to have the sum from I equals 1 to n of a y I b theta plus n c theta plus the sum I equals 1 to n b by I. All right, so that means that our log likelihood should be the sum from I equals 1 to n of y to the negative y to the lambda multiplied by negative theta negative lambda plus n log lambda minus lambda log theta plus the sum from I equals 1 to n lambda minus 1 log y. All right. Okay, so now, given that we have the log likelihood function, and there's actually a variety of ways that you can get to the solution. You could also find the log likelihood function by first computing the log likelihood and then finding the log. So we can check this. Right? So we can verify our results using the exponential family relationships by using the classical approach for finding the log likelihood, which would be just to take the product of the densities and then take the log of that result. And these should end up at the same value. It's good practice too to go through this, as this is the standard approach for finding MLEs for most distributions. So I'll leave that as an exercise just for some practice. Okay, so the next thing we need to do is find the score function for theta, which was the original purpose of this problem. So S of theta is going to be equal to dl by d theta. So it's simply the derivative of our MLE with respect to theta. All right, so this thing, starting with the first term. So the first term is already kind of a pain in the ass, but we have y lambda to the negative theta minus lambda. So we're taking the derivative with respect to theta. So this should be negative lambda y lambda multiplied by negative theta. Or actually, sorry, let me just do it in a more straightforward way. So we're going to have y lambda, then we're going to have negative lambda multiplied by negative theta to the negative lambda minus 1. Okay. And then we can simplify this after. Okay, and then the next term is going to cancel out because the derivative of n log lambda with respect to theta is going to be nothing. And then we're going to have minus n lambda over theta. And then the last term will also cancel out. Okay, so this thing should simplify to the sum from I equals 1 to n of y lambda and then minus, or no, this is going to be plus now. Oh, no. Y lambda lambda theta to the negative lambda minus 1. Sorry, yi, lambda times lambda, yep, to the negative theta minus 1 minus n lambda theta. Okay, and then we would say to find, actually, I think I might have that. Yeah. Okay, and then this would be what we are looking for. Okay, so that's our score function. This isn't a proof. Okay, so this is our score function for this problem. Okay, any questions so far? No, it's not. So you, like, technically, just for clarity, if we wanted to, you could put this last term in the sum. You just have to factor the n out. So this would be equivalent to the sum I equals 1 to little n of yi to the lambda over theta to the lambda plus 1 minus lambda theta. So if you wanted it in the sum, this would be the way that you could write it. So that leading n is due to the sum. Does that make sense? Okay. Any other questions before we move on? Okay. You can ignore my chicken scratch for now. I'll go through this momentarily. Just making some informal notes, very unprofessional. Okay, so traditionally, or not traditionally, but what we would do next is set the square function equal to 0 and solve for theta. Okay, so we're going to take our expression from the previous slide in either form, set this thing equal to 0, and then try and solve for theta. In this particular illustration, it should work out that solving for theta using this expression is not going to be possible as it's written. So we need to then use an iterative procedure. So if you can solve it directly to find the MLE, you're free to just use that estimate. If you cannot, that's when you would need to use an iterative procedure. So we're now pushing forward under the assumption that if we set S theta equal to 0, we're not going to be able to find a direct solution for theta. So what we're going to do instead is use a Newton-Raphson. So we're going to define our two Newton-Raphson algorithms for this approach. Okay. So first off, recall that theta on iteration k is equal to theta on iteration k minus 1 minus the score function evaluated at theta at k minus 1 divided by the score function, the derivative of the score function evaluated at k minus 1. Right, so this is our first definition for the Newton-Raphson. Okay, so we're going to look at two different ways of formulating the Newton-Raphson. This is the first one. So we already have the score function. All we have to do is essentially sub in theta k minus 1 into that value. So that's very easy to do. So we don't need to worry about that, but we know from the previous slide what the score function looks like. What we need then is the derivative of the score function. Okay, so we have S of theta. We need S prime of theta. Okay, so this is simply the derivative of the score function. So S prime theta is equal to d by d theta of S theta. So this is going to be d by d theta of the sum from I equals 1 to little n, this thing. All right, let's see if I can figure this out. So we are going to have the sum from I equals 1 to n, yi to the lambda And then we're going to have negative lambda minus 1 times theta to the negative lambda minus 1 minus 1 minus negative 1 n lambda theta to the negative 2. Sorry, I apologize for switching between the exponent and the fraction notation. I just find it a bit easier to work with the exponents. All right. So that should give us the sum from I equals 1 to n. Oh, and I'm going to call this equation 2. The sum from I equals 1 to n of yi lambda lambda times lambda minus 1 I think that's good. Yeah. Okay. All right. So this, and then this is our expression for the second derivative. Okay. So the process from this point, actually the hardest part is this deriving the score function and the derivative of the score function. Because at this point, what we are able to do is just take a value for theta, sub it into S prime of theta and sub it into S theta. And what we get out is a result for theta k minus theta k. So we start at some initial quantity. We take that initial quantity and plug it into the score and the derivative of the score function. We get some value out. We take the ratio of the value, subtract from the initial quantity, and then we update to get the new value. And then we take the new value and plug it back in again. Okay, so that's the first Newton-Raphson based off of the score and the derivative of the score. And we're going to look at both of we're going to look at this in detail in the lab when we can actually work through the process in R and look at how the calculations are being performed. Does anyone have any questions? Okay. Okay, so that's the first Newton-Raphson. Here's the second. Oh, sorry, and these should be hats. Right. Obviously. So these are all functions of estimates, not the true value. All right, so the second function says take the guess or the initial, take the value on theta at iteration k -1 and add the score function over the information function. Okay, so we already have the score function. So what we need is the information function. Right. So the information function for theta right? Okay, so recall the information function for theta is given by b double prime theta no, this would be theta hat, right? Yeah. So b double prime theta times c prime theta divided by b prime theta minus c double prime theta. We need, okay, so this is from lecture set number 2. And actually, sorry, in this case, we also need the sum because we have to include the data. So it's going to be the sum. All right, so the information function again is essentially just it's the expected value of the derivative of the score function, but we worked out an expression in terms of the exponential family components. So we're going to use that to kind of highlight the benefit of having things in that approach. Okay, so that's where my chicken scratch below comes into play. So I was just making sure I could work these components out. So I'm just going to rewrite this here. So we need double derivatives with respect to b theta and c theta. So we have b theta is equal to negative theta minus lambda. And we have c theta is equal to log lambda minus lambda log theta. Okay, so this is actually very easy to do if you sub in. So note that in this illustration, we are going to let lambda equal 2. So in the expression we found above and in the expressions that we're working at now, we can just sub lambda equal to 2 in all those cases, and we're going to get more simplification. That being said, it's a little trickier to do it without the 2 being subbed in. So I'm going to try and do it that way, which is what I was doing before. So for b prime theta, we're taking the derivative with respect to theta. So this is going to be lambda times theta to the negative lambda minus 1. And then for b double prime theta, we'll have lambda negative lambda minus 1 theta to the negative lambda minus 2. All right, and then for c prime theta, we're going to have negative lambda to the theta minus 1. And then for c double prime theta, we're going to have lambda to the theta minus 2. So not terribly tricky, but a fair challenge, I suppose. Okay, so therefore, I of theta hat is going to be the sum from I equals 1 to n of lambda negative lambda minus 1 times theta to the negative lambda minus 2 multiplied by negative lambda to the theta minus 1 divided by lambda to the theta to the negative lambda minus 1 minus lambda to the theta minus 2. All right. Okay, so this is where the fun part begins. So now what we need to do is try and simplify this thing. Again, if we just plug in 2 for all the lambdas, the simplification of this becomes a lot easier. But let's just see if we can make some substitutions here. So the first thing I think we can knock off are the lambdas. So you can see there's a lambda in each term on the top. So if I divide by lambda, I should get negative lambda minus 1, theta to the negative lambda, theta to the negative 2, minus lambda theta to the negative 1, divided by theta to the negative lambda, theta to the negative 1, minus lambda theta to the negative 2. Sorry. That looks terrible. Okay, I'll clean this up after. I'm just trying to make myself a little bit more room here. Simplify this thing. Pressure is on. All right, so Looks like we can drop those theta to the negative lambda. We can drop that theta to the -1 as well. So let's see, sum I equals 1 to n. So we're going to have negative lambda minus 1. So -2 plus 1. So that's going to be theta to the 1, negative lambda theta to the -1. Minus lambda theta to the -2. Oh, sorry. So then we're going to have oh yeah, very close now. Okay, so then what we're going to get is lambda squared theta to the -2 plus lambda theta to the -2 minus lambda theta to the -2. So that's going to give us the sum from I equals 1 to n of lambda squared divided by theta squared. Or no, sorry, I'll just keep it in as required. Nice. Okay, sorry, and I apologize for this. I'll just try and clean this up really quickly here. Okay. Okay, and then that's our expression for the information function. So then same idea as before. So now we're just going to take our estimates and we can plug them into the score, and then we can plug it into this information function directly. And then we can find our little nudge factor, add that to theta, and then take that new value, replug it in, nudge factor, add it, and continue to cycle like that. Okay, any questions? Sorry, and again, I'll just say before the question, again, the purpose of this is to show how to formulate the Newton-Raphson. So these are two different Newton-Raphson algorithms. The goal is exactly the same. And given that the goal is the same, they will likely converge to the same value. But it's always nice to have different formulations of things, because then you also get a check. So if they converge to the same value, it gives us a little bit more certainty in the result, right? So we can either do nudge, we can either subtract the ratio of the score divided by the derivative of the score, which is equation 2, or we can add the score divided by the information function evaluated at our current estimate, and that's 3. But what we had to do is actually work out the forms for the score and the information. Any questions? It's not a question, man. Just kidding. Equally valuable. What would be the answer to that? All right. Okay, so now that we have our Newton-Raphson set up, or at least we understand how to set them up, here is what would happen for this particular problem. And again, we're going to go through this in lab where we can actually look at the steps individually, and I'm going to show you how to formulate this. But we have let theta 0. So we're going to take a starting value equal to the mean of the data. So I'm just computing the sample mean for those 49 observations that were given at the start of this example. And what I'm doing then is I'm taking that value and I'm plugging it into our two different formulations for the Newton-Raphson. So theta hat from 2 represents when the nudge factor is the score function divided by the derivative of the score function. And equation 3 is when the score function is divided by the information function. So you can see that the two iterations the two approaches on iteration 1 give different values. This is to be expected. On iteration 2, we still have different quantities. On iteration 3, you can see that they're starting to move towards the same point. And then on iteration 4, they are equal. And then we can say that this has converged around iteration 4, given that there's no change in theta hat, at least to 3 decimal places on iteration 5. So the algorithm converges quite quickly to a solution. And both approaches are estimating that the MLE for theta is 9,892.177. So this is our estimate for theta in the Weibull for the Weibull distribution that we are fitting to the data. Given the 49 observations, we can compute the actual likelihood surface using the log likelihood function that we drove or that we structured when we found the score function. So this curve represents the surface of the log likelihood function. So basically all I did here is I wrote a function to compute the log likelihood based off what we did in lecture. And then I plugged in a variety of values for theta. I think I generated theta between 7,000 and 13,000, and then I varied them by like 0.1. So I have this nice smooth surface or representation of the log likelihood function. And then what I did is I found the value that maximizes the log likelihood. So this point here, 9,892.2, this is the value of theta that gives us the highest point on this surface. So you can see that our estimate from the Newton-Raphson, which is 9,892.177, is right in the ballpark of where it should be. If I were to stagger the sequence even more, so perhaps I zoom in on this likelihood surface and then I stagger the values of theta by 3 decimal places instead, I would imagine that we're going to get very close to what we found from the Newton-Raphson. But to 1 decimal place of accuracy, I think we can all agree that the estimate of 9,892.177 is a very good estimate, given that for this data, the actual value to 1 decimal place is 9,892.2. So this is essentially just verifying that the result we got from our Newton-Raphsons for this particular illustration are very good, if not excellent. And then the negative 480.8449, that's the maximum log likelihood value for this particular data set, given a Weibull distribution with lambda equal to 2. Any questions? All right, so what we are going to do now is take this iterative idea, so this Newton-Raphson idea, and try and generalize this to a generalized linear model. So we're going to try and determine a general strategy for fitting generalized linear models to a particular data set. And we are, like we would be in the case of the normal linear model, our interest is now going to shift to estimating the coefficients of the linear component of our GLM. Okay, so just as a reminder, recall that if y1 to yn satisfy the properties of a GLM, so they belong to an exponential family that's in canonical form, and there's some link function that can connect the linear component to the response variable, then the expected value of y is going to have representation negative c prime theta over b prime theta. So this, we drove this last class. So this is the general expression for the expected value of y from an exponential family. Variance of y has the expression given in the second equation. And then we assume that there's some there's some monotonic function g that links the expected value of y to this linear component. Our objective is to estimate beta. And we're going to take basically the same steps that we just highlighted in that particular example. So we're going to start by trying to work out the score function for beta, and then we're going to try and work out the information function for beta, and then we're going to try and develop a general iterative procedure to estimate beta given those components. All right. Now, we've already seen an illustration of this, but it's also worth recalling that the likelihood function for yi can be represented as shown at the end of slide 13. We have a similar representation shown before. One, note that here I have pulled the sums out front of the theta I for C and D. Given that these are only functions of theta, you could also write them as nc theta I or nd theta I. But if there are components that are attached to y that are included in these, then actually, I think this is a mistake. Yeah, sorry, this is not a theta. Right, so if there's nothing, the c theta I could also be written as nc theta I, and the d is a function of yi, so the sum has to be there. Okay, so our objective is to work out expressions for the MLEs for the coefficients of the linear component in the GLM, so beta 1 through beta p. To do this, we require the score function for beta j. So we're going to work through the process of deriving that score function now. So S of beta j is equal to d by d beta j of the log likelihood of theta given y, right, from above. So this is just this thing right here. Okay. So this can be written as the sum from I equals 1 to little n of d li divided by d beta j. And this can be written as the sum from I equals 1 to n of d li d theta I times d theta I by d mu I times d mu I by d beta j given or by the chain rule. Okay, so that's the first part. So we now have a sort of a general open expression for the score function, and it's the product, the sum across the product of each of these partial derivatives. So the next thing that we're going to do is derive the partial derivatives of, or show how we can represent the partial derivatives of these function, of this function. Sorry, any questions? So each partial derivative can be expressed as follows. All right, so starting with dLi by d theta I. So what we're doing now is basically just taking the derivatives of the components of the exponential family, right? So this thing can be written as yi b theta I plus c prime theta I. And this can be written as b prime theta I multiplied by yi minus the expected value. So that's kind of a cool little representation. You can see here that we're using that expression for the expected value that I gave at the top of slide 13 to find the expected value of yi. So we basically have kind of like a scalar multiplied by y minus its mean. It's kind of like a variance representation in a way, but we're missing the square. Right. Okay. D theta I divided by d mu I can be written as 1 divided by d mu I over d theta I. D mu I over d theta I can be written as c double prime or negative c double prime theta I over b prime theta plus c prime theta I times b double prime theta I over b prime theta I squared. Okay. And that's a quotient rule for the expected value. So we're taking the derivative of the expected value formula with respect to theta I, and this is the result from the quotient rule. Right. And then this thing, this is a comma. Okay, so then this thing, so you can see here that we have a representation of the variance formula now. Well, sort of. Okay, so this thing would be minus, or sorry, would be equal to b prime theta I times the variance of y. Any questions so far? Okay. So the last one is d mu I by d beta j. Okay, so this is going to be equal to d mu I by d eta I multiplied by d eta I by d beta j. Okay, and then eta I is basically equal to that linear component. So this is going to give us d mu I by d eta I multiplied by dx ij. And so that's the derivative multiplied by xij. Okay, so therefore, S of beta j is going to be equal to the sum from I equals 1 to n of yi minus mu I divided by the variance of yi times xij multiplied by d mu I over d beta j. And it follows that the solution to this is going to give you the MLEs for beta j. Okay. So it follows that the solution of this will give the estimate for each beta j for j equals 1 to p. Any questions? Okay, so the next thing that we're going to do, again, so the objective right now is to try and work out a method for evaluating these MLEs. So we're trying to basically find kind of like our own version of the Newton-Raphson for for fitting a generalized linear model. All right, so we have the score function sorted out. We know what we need to do with the score function, which effectively means like we need to set this thing equal to 0 and solve for the beta j's. in order to do that, it's pretty clear just from looking at it that this isn't going to be able to, we're not going to be able to do this through like a closed form expression. So what we have to do is take an iterative approach to find these estimates. So we're essentially going to structure like our own Newton-Raphson in this case, or a general Newton-Raphson for the GLMs. So we have the score function. We know that the first thing we can do is take an initial guess at the value of the beta j, and we can plug it into this score function, and then we can get out an estimate, or we can get out a value for the score function. The Newton-Raphsons, there's two types. So we can say, take the score function at beta j and divide by the derivative of the score function at beta j, and then use that to nudge your estimate. Or we can take the score function at beta j and divide by the information function at beta j, take the ratio and use that to nudge the estimate. So we're going to work through the second approach. We're going to derive an expression for the information function, and then we're going to establish what our Newton-Raphson algorithm is going to look like for these beta j. So we have our score function. Before we derive the information function, we just need to quickly refresh what a variance-covariance matrix is going to look like. So we're going to derive this expression in terms of the vector for beta rather than each individual beta j. So just as a reminder, a covariance matrix for a random vector is a p by p matrix where p is the dimension of the vector. The diagonal elements of that matrix are the variance for each component of the vector. So you can see here we have the expected value of x1 minus we have the expected value of x1 minus its expected value times x1 minus its expected value. So that's the definition of variance. And then the off diagonal elements represent the covariance between the each component in that vector. So the covariance matrix itself is useful because we have the variances along the diagonals, and then we have these covariances on the off diagonals, which give us a representation of the relationship. If we scale the covariance matrix, we get what is called a correlation matrix. The correlation matrix is a little more useful in terms of the off diagonal elements because we know that these are all standardized between -1 and 1. So that gives us more interpretation as to how strong that relationship might be. Whereas when we're working with the covariance matrix, there's no real limits on those values. So what high and what low is a little bit more unestablished, I suppose you could say. Okay, so we're going to let uj equal the score function, and we're going to let I of beta j equal the variance of the score function. So that's the information function. So the information function for u is therefore going to essentially just be a covariance for u. So it's going to be following from the definition of the covariance for x. The diagonal elements are going to give the variance of each component of u, which is the score function of beta j. The off diagonal elements are going to give those covariances. We know that, in terms of the off diagonal elements, the expected value of u1 squared and the expected value of uj squared is equal to 0. I think we either showed that in lecture set 2, or I was leaving that as an exercise. Either way, we can show that the expected value of the square of the score is equal to 0. And therefore, our information matrix simplifies to just being the variances on the diagonals and then the expected value of the products on the off diagonals. And that's because the expected value of the score is 0. And therefore, the expected value of the score squared is also 0. Right. That makes sense? Any questions? Bit rambly. Bit more rambly than I would have liked. Okay, so we are going to show, or basically what we're going to do now is derive an expression for the information function. We know that the information function, well, we know what the expression for the diagonal elements is going to look like, since we've already found the variance of each part of the square function. So we actually have the diagonal elements already. So we've done this, we did this last class, and we actually saw an example of this already because we did it for theta in that opening Newton-Raphson example. So in terms of finding the information function for the vector u, so the vector of score functions, we know what the diagonal elements are going to look like because we know how to derive the variance of the score function. We've already done this in the general case. So now all we need to do is find the off diagonal elements of this information, or of the information matrix for the vector u. Okay, so we should write, we have already found an expression for the variance of the score function. And we did this in lecture set 2. And we used it already today. Right. So we know how to compute the diagonal elements of this information function. So we only require an expression for the off diagonal elements. Expected value uj uk for j k equal 1 to p such that j does not equal k. All right. So again, what we're trying to do right now, work out the information function for the vector of scores. We know the diagonal elements because we've already found that expression in previous work. We did that on slide 14 of lecture set 2. So now we're just trying to find the off diagonal elements. Okay, so we are going to have the expected value of uj uk is equal to the expected value of the sum from equals 1 to n of yi minus mu I divided by the variance of yi multiplied by xij multiplied by d mu I over d theta I multiplied by the sum from I equals 1 to n. And then, or sorry, the sum from L equals 1 to k. Or sorry, to n again. Maybe I shouldn't use I, J, I already have, K I've been using. Just need another indicator here. L, that symbol, okay, this is a lowercase l equals 1. Yeah, it doesn't look. We'll just say H. H equals 1, that'll work. Okay, and then we're gonna have YH minus mu H over the variance YH X HJ D mu H over D eta H I think I got everything. Okay. All right, so then this becomes the expected value from the sum I equals 1 to n of the expected value of yi minus mu I squared divided by the variance of yi squared xij xhj. Oh, sorry. There we go. Multiplied by d mu I d eta I squared and we can say this is equal to the sum from I equals 1 to n of xij xik divided by the variance of yi d mu I d eta I squared. And then we can say that this is going to be the information function for beta j. For each beta j. Right. So therefore, we can write that beta on iteration k is going to be equal to beta on iteration k minus 1 plus the score function for beta at iteration k minus 1 divided by the information function for beta at iteration k minus 1. Oh, hat, hat, hat. All right. Okay, so I'm going to stop here because we have to, there's a little more derivation that's required. And okay, so what we've done today is looked through an example of a Newton-Raphson algorithm. So we basically formulated two Newton-Raphsons, and we studied the results from those two Newton-Raphsons. What we did after that is we drove an expression for the score function of beta j, which we need to find MLEs for beta j. We noted that we can't find the result in a closed form method. Like in the general case, there are situations where they will be closed form. For example, if you use the normal linear model example to follow. But we drove a general expression for the score function of beta j, and then we drove a general expression for the information function for beta j. And what we have done now is found how that information function is going to be structured in terms of the diagonal and off diagonal elements. Okay, so we have here the, oh, sorry, this is not correct. Yeah, this was a bit confusing. Okay, so what we have here now is an expression for the off diagonal elements of that information function, and we know what the diagonal elements are going to be because we've deriven those in the past, or we drove an expression for that in the past. Okay, so now we have this Newton-Raphson style algorithm shown here to find our MLEs for beta k, and we understand that this is going to be iterative, and ideally convergence to solutions will be quick, and we'll see varying examples of this throughout this semester once we start looking at specific examples of GLMs. So what we're going to do next class is continue with lecture set 4. So now we're going to derive the actual iterative weighted least squares approach, which is the approach that's used for GLMs. And then we're going to look at an example of how this would work. Because we didn't get to the example today, I won't include it in the lab tomorrow because otherwise we're going to see the illustration before we go through the theory. So I'm going to push that to next week. As a result, tomorrow's lab is not going to be very long in terms of learning material. What we're going to do is look at illustrations of how to code a Newton-Raphson based off what we did in class today. And then I might dig up another example just so that we can look at a second one to give a little more illustration because we'll have time. So tomorrow's lab, I'm going to go through how to code a Newton-Raphson in R and some of the background R functions that you would need in order to do this, or sorry, some of the background basic R understanding that you would need to be able to do this. Most of you have seen this before, but just for completeness sake and under the assumption that not everyone has coded their own functions in R, I'll go through that process with you. And then the rest of the lab period will be time to work on the first assignment, which is due on Friday. Okay, so we're going to continue with the lecture set 4 or lecture set 3 and move into lecture set 4 on Thursday. Tomorrow, we will look at examples of coding Newton-Raphsons in R based off what we did in lecture today. Assignment 1 is due on Friday, and I have office hours tomorrow morning. So I will stop there. If there's any questions, I'll hang around, and otherwise I will see you guys in lab tomorrow.